Good morning all of you. So we have completed nearly about 10 classes so far. I hope most of you are following what is happening in all these 10 classes, and I think the first tutorial is due on 14th of this month, and I will also most likely early next week upload the second tutorial on similarity solutions. Okay, so most likely we will complete the similarity solutions in the next couple of classes and start the integral analysis for external flows. Okay, so we have quite a few topics to cover, so I have to move a little bit fast, and I hope your earlier knowledge of fluid mechanics will help you in covering all the things that we won't be discussing here. Okay, so let us continue with the Falkner-Skan similarity solutions that we had derived yesterday. These are for flows with pressure gradient, and the final similarity differential equation appears in this particular form, and these are the boundary conditions. And once again you have to use the shooting method to solve the ODE numerically. I have also given you the 3 first order ODEs to which it can be reduced, and the same boundary conditions like that of the Blasius equation. So once you solve this okay, so one more thing is that so these are some of the velocity profiles if you solve the ODE by the shooting technique, and this is how the velocity profiles look, and these are the similarity profiles. So I am plotting eta on the y axis and f prime, which is nothing but the non-dimensional velocity on the x axis, and I can substitute different values of m into this, and for each value of m I can solve the ODE by shooting method, and I can plot the profiles. For example, m equal to 0, this is the flat plate case. You get a profile something like this, exactly similar to the Blasius profile, and for positive values of m greater than 0, so say like 0.33, something like this, so 1, it is something like this. So if you look at m equal to 1, this is the stagnation point flow, right, and this is your flat plate. All right. Okay. So therefore, if you look at your values of m, which are basically increasing, okay, so the profiles are in this particular fashion, and for the values of beta, the wedge angle, I mean, let me once again draw the representation so that you can understand. Okay, so can you tell me how the m and beta are related? Or beta pi is your wedge angle, beta by 2 minus beta. Okay, so for negative values of beta, that is, I was giving an example, when you roll this in the anti-clockwise direction, so that they both coincide, that is the m equal to 0 case, and if you roll it further, roll this particular surface further down, it becomes negative. Okay, for the negative values, typically if you make it more and more negative, you will get adverse pressure gradient flows, right, the example that we have seen yesterday, and for a particular value for m, which is exactly minus 0.091, you will see the flow is separating. Okay, so at this particular location, the boundary layer theory will not be valid anymore, so there is no point in going further less than minus 0.091. So this is the limit of m, where you can, up to which you can go negative, and the value of m up to which you can also go on the other side. For typically we are more interested up till the stagnation flow, so we can go up to m equal to 1. Okay, so what is happening to the velocity gradients? So typically if you want to calculate say du by d eta, as you keep increasing your m, what is happening to du by d eta? Smaller? So typically if you are saying, okay, so I say this is my eta range, okay, if you compare 0.32, so this is my change here, okay, this if I look at f for these values, so in which case your gradient is higher, whether is it for 0.32 or whether it is for, so here in this case your eta values are, this is your d eta here for this value of df prime, and this is your d eta here, okay, in which case the d eta will be more for this case, so therefore in which case the gradient will be higher for this case, okay. So as you keep increasing your m, okay, the velocity gradients become more and more steeper, okay. So therefore so this is to do with the particular kind of flow that you are looking at. So typically what you can do, I will give you some problems where you can substitute the corresponding configuration according to the value of m, and you can get these profiles, and you can try to see how the variation in the slope appears to you. Okay, so this is all with respect to the solution. We are more interested in the derived quantities like the skin friction coefficient for the flow as far as the flow is concerned. So we can calculate the skin friction coefficient locally. So this is nothing but nu du by dy okay. Now if you substitute everything in terms of the similarity variables, so you will be getting an expression which is like this in terms of f and eta, okay. So this depends on the curvature at the wall, this by now you all know. For the case of flat plate, the value of this is 0.332, so this leads to the familiar expression Cf is 0.664 by square root of Reynolds number, okay. So now all we need to know is for a given configuration what is this curvature at the wall. Once we know that, we can calculate the skin friction coefficient locally for that particular configuration. So once you solve the equations by the shooting method for different values of m, we can have a nice tabulation where we can tabulate the curvature terms for different configurations. So for the value of beta, this is the value of m, and this is d square f by d eta square at eta equal to 0, and this is the particular configuration or case that it corresponds to. Okay, so beta equal to 1.6, okay. So 1.6 times pi, so you will find that this is something like this, okay, or maybe you can say it becomes like this. You have a flow which is like this, right? It's much more than 1, so it's much more than, so your wedge angle is more than pi, alright. So in this particular case you can have flows like this, and the corresponding value of m will be equal to 5 if you substitute into this expression, okay. If you compute the slope, the curvature at the surface, this will be 2.6344 exactly. In fact, you can do it, in fact I will give you an exercise where you can do it and compare with these values, okay, you should be getting the same values. And now the case of beta equal to 1, m equal to 1 and 1.2326, what is this case? Stagnation flow, alright. So beta is 0.5, m is 1 over 3, and the corresponding value is 0.75746. Beta equal to 0, m equal to 0. What will be the value? 0.332. this is the flat plate, and point 0.14, the corresponding value of m will be minus 0.0654, and the corresponding value is 0.16372, okay, and finally minus 0.1988, okay. Corresponding value of m, can you guess what is the corresponding value of m? Minus 0.091, okay, that is this particular case that we have. So what do you think will be the curvature for this? This is a separated flow, okay. At the point of separation, what is the slope? What will be du by dy for separated flow? So if you have a flow, suppose you have a gradient like this, and here you plot, you have profile like these, okay. Now at the point of separation, the profile becomes like this, and after that, in fact, this will be like this, okay. So this is dp by dx greater than 0, okay. This is separation point, this is separated flow. So you can visualize the flow coming like this and at this point detaching, and then you have a nice big separation bubble here, okay. So how do you check that flow has separated or it's about to separate? What is that? Not curvature. First you go to the first derivative before you go to second derivative. Du by dy for the separate, for a condition. What is the condition for separated flow? Du by dy at y equal to 0 equal to 0. This is the case, okay. Once it is separated, what is the condition there? It should be negative, okay. Therefore, what will happen to curvature when it is at the separation state? 0, right? So this has to be 0, and this is a separation case, separated flow. Alright, so I think this is giving you a final summary. And special case where we can apply the stagnation flow, if you look at flow past a circular cylinder, okay. So this is your radii r, and this is your approaching free stream velocity, which is constant, and then the free stream, now when it travels over the surface, it becomes a function of your local coordinate x, and where x is defined in this particular fashion, okay. That is the sector location, sector distance starting from this point where it is 0, okay. So if you look at the case of flow past the circular cylinder, from the potential flow theory, you can actually calculate how the u infinity is varying locally, okay. So the profile is given, I think you must have studied this in your incompressible flow course. So u infinity by u, any guess how it varies? If you go along the periphery or the circumference of the particular cylinder, how does the local free stream vary? what is the value of velocity here? It has to be 0. And where does it reach maximum? Where your theta equal to pi by 2, okay, and x is equal to r theta basically. So x by r should be equal to pi by 2. At that location it becomes the maximum, okay. So it should be a sinusoidal variation, okay. Only you have sine 0 is 0, sine pi by 2 is 1. So if you say u infinity x by u infinity, it has to be a sine variation, and what should be the variable? X by r. Alright, maybe I can use a capital R because this is your radii of the cylinder. And what factor should come here? At x by r equal to pi by 2, this will become 1. Does u infinity become u infinity there? It should be 2, because it becomes exactly twice the, because it has to accelerate again from here. Once it accelerates, it has to go more than the free stream velocity there, okay. So this is your inviscid velocity profile for a circular cylinder. Now if you are looking at region values of x which are very small, that means close to the stagnation region, okay. So then you can approximate this sine x by r as simply x by r for small values of x, okay. So for small values of x by r, that is close to the stagnation, you can write your u infinity by constant free stream velocity as 2 x by r, okay. So therefore if you compare this with your Falkner-Skan form of velocity profile, which is like something like u infinity of x is c x power m. So what can you deduce? What should be value of m, what should be the value of c if you compare these two? C is equal to 2 u infinity by r, okay. And what is the value of m? 1, okay. So therefore this profile will be something like okay. So what kind of flow does it mean? Stagnation point flow, okay. So when you are looking at region close to the stagnation, even for a curved surface like cylinder, okay, you can approximate the flow pattern to be similar to the stagnation point flow, for which we have already calculated the profiles and the curvature at the wall, okay. So this is a very important thing. So it does not limit, the Falkner-Skan solution does not mean it is only applied to a wedge configuration like this. It can even apply to any stagnation flow, even for a bluff body like this. It does not need to have a sharp corner, okay, provided you are looking at only region close to the stagnation region. So if you simply use c equal to 2 infinity by r, so this is nothing but the stagnation flow, okay. The same solution will hold for the cylinder also as well. Okay, so this is a very important useful correlation, because to calculate, for example, the heat transfer in the stagnation region of a cylinder, you can solve the energy equation from the Falkner-Skan solution, and you can apply that to get the local Nusselt number profiles for the cylinder, okay. Okay, so for small values of x, your sin theta can be replaced as theta, right, okay. So therefore now we will move on to the heat transfer problem. So the boundary layer energy equation, when you write it down for the flows with pressure gradient or without pressure gradient, they are both the same, okay. So without the viscous dissipation term, this is your energy equation where your theta is defined how? T minus Tw by T infinity minus Tw. So I want my temperature profile to look identical to the velocity profile, alright, and the boundary conditions at y equal to 0, your theta should be, it should be 0. Okay, if I had defined my theta this way, okay, it has to be similar to the velocity profile, right? So at y going to infinity, theta should be 1. Okay. Now what I can do from the definition of the similarity variable that I use, also from the definition of stream function, which is a function of the similarity variable, I can plug in for u, v, convert all x and y in terms of eta. Okay, the same way that we did for the Blasius energy, you can apply that here, because it is no different, and except that when you write the similarity variable eta, here this is a function of u infinity of x by nu x, rather than simply u infinity in Blasius. So when you differentiate this with respect to x, you have to be careful now, you have to account for the variation of this. So you can substitute cx power m, okay, and then you can differentiate it. Okay, so for example, if you say that this is y square root of cx power m by nu x, so this can be written as y square root of c by nu into x power m minus 1 by 2. Okay, therefore if you say your d eta by dx, so this will be y square root of c by nu into m minus 1 by 2 into x power what? If I differentiate, what should I get? Exponent m minus 3 by 2, so I can write that as m minus 1 by 2 minus 1. Okay, so once again y c by nu x power, so this entire thing is what? Eta. So this will be m minus 1 by 2 into eta by x. Okay, so you should take care when you are differentiating and transforming the variables, now that your free stream velocity is a function of x. Okay, so appropriately you do all the substitution and transform this in terms of the similarity variable and everything in terms of f, and you will get the similarity equation for energy, d square theta by d eta square okay. So this is your energy equation. Okay, for the case of m equal to 0, this reduces to the flat plate energy equation, similarity solution. Okay, so additionally here you have m plus 1 by 2 because of the factor of m which comes in the free stream velocity. Okay, if you substitute all of that, you will definitely be able to reduce this. And the boundary conditions as eta going to 0, theta equal to 0, eta going to infinity, theta equal to 1. All right. Okay, so once you know the flow, you know the value of f, you plug it in. For a corresponding value of m, you can solve this once again by shooting method. Okay, the same way that we have been doing, and you can get the profiles for theta as a function of eta. Alright, so the same procedure repeats here. Now what I am going to give is just the way we tabulated the curvature at the wall for the velocity profiles. I am going to give you, once you substitute and get the values, you can get the slope of the temperature at the wall for different values of m. okay, for different configurations how does it look, because this is required to calculate the Nusselt number. Nusselt number depends upon this temperature slope at the wall, okay. So if you do the tabulation, so d theta by d eta at eta equal to 0, okay. So m, the Prandtl number. Now you should realize the temperature profiles are now function of your velocity profile, your Prandtl number and your m, okay. So for a given value of m, you know the velocity profile, put that function, the value of m and also the Prandtl number which you want to calculate. So both of all the three have to be simultaneously fixed. Of course if you fix your m, you fix your f also, okay, and also you have to decide which Prandtl number you are calculating. So you can tabulate this for different values of Prandtl number. So for m is minus 0.0753, okay. Okay, I am just giving you some value of m here, for which if you have Prandtl number of 0.7, this value becomes 0.242, okay. I am just tabulating all the values here. Okay, so anybody remember now value of m equal to 0, flat plate, what should be the value at Prandtl number 0.7? Probably I must have, yeah, I think you can calculate and tell me. What should be the value of d theta by d eta for Prandtl number 0.7? Okay, so for Prandtl number of 1, what should be the value? .332, why? Yeah, because for the case where your Prandtl number equal to 1, I mean the velocity and the temperature profile should be identical. So the curvature d cube d square f by d eta square should be exactly equal to d theta by d. So this should be 0.332. So this value should be 0.332 into Prandtl number power 1 by 3. Okay, so what should be the value? So it will be something like 0.292, it will be reduced. So then this is 0.307 and 0.585, this is 0.730. So on. So if you go to m equal to 1, the stagnation flow 0.496, 0.523, okay. So these are some kind of values. I am just giving you this because tomorrow when I ask you to compute using the shooting method, you should be able to match with these tabulated values, alright. So why we are calculating the slope? Okay, so because we finally are interested in the heat transfer coefficient and Nusselt number. So therefore you can define your local heat transfer coefficient the same way, the wall heat flux divided by T wall minus T infinity. Okay, if you substitute for minus k dt by dy at y equal to 0 and write in terms of d theta by d eta, you should get k T wall minus T infinity into, so you can write your dt by dy as d theta by d eta at eta equal to 0 into d eta by dy. okay, which is nothing but square root of u infinity by nu x divided by t wall minus t infinity. Okay, so finally if you define your Nusselt number, local Nusselt number as hx by k, so that will result in d theta by d eta theta equal to 0 into, so you have x here, so square root of u infinity x by nu, which is nothing but your if you multiply h into x by k, so what happens to this particular term? Reynolds number, square root of Reynolds number. Okay, this is the same as what we did for the flat plate. Okay, there is nothing new here. Only thing you should now know for which configuration the value of d theta by d eta you have to pick, put it there, and then you will get the Nusselt number profile for that particular value of m. Okay, and also now it is a function of Prandtl number. So you may have to fit a curve as a function of Prandtl number, and you should bring the Prandtl number dependence. Okay, now for the stagnation point flow, if you are interested in values of Prandtl number about 1, okay, that is something in this particular region right here, okay, you can in fact fit a curve to the values of d theta by d eta in this Prandtl number regime close to 1, and you will get a nice curve fit of this particular form, which is 0.57 times Prandtl number to the power 0.4. Can you just check, can you substitute Prandtl number as 0.8 and check whether you are getting something close to 0.523? Okay, so this is the kind of fit that you can do for m equal to 1 around Prandtl number close to 1. Okay, so you are not saying here Prandtl number is exactly 1, it has some Prandtl number dependence, but I mean the dependence is relatively kind of similar, you have about 0.5 to 0.57 variation here. Okay, so therefore if you substitute for that, so your d theta by d eta is a function of Prandtl number now, this becomes 0.57 into Rex power half Prandtl number to the power 0.4. So this is the case for m equal to 1, Prandtl number close to 1. Okay, so this is the local variation that you find for the stagnation point flow case. Of course, you know the variation with respect to Prandtl number for m equal to 0. Pohlhausen already did that. He did the curve fit for different values of Prandtl number, small Prandtl numbers, intermediate and large, and you can use those values. Okay, does it make sense? Okay, so that this is a reasonably good fit, okay, for Prandtl number close to 1. Okay, now so this is one example to show you for the stagnation, for example stagnation flow, how we can define the local variation in Nusselt number. Okay, so all this can be also equally verified by you. You can calculate the values of the slope, compare that for different values of m and Prandtl number with the tabulated values, and you can yourself correlate with these values right here. Okay, so now one more thing, as we said, if you look at the flow past a cylinder, okay, the flow that we are looking at right here, so apart from u infinity, suppose you heat this particular surface, so you are maintaining this at T wall equal to constant. Okay, so this is a flow. Apart from the flow, you also have a temperature profile. Okay, now this u infinity is a function of x here, whereas still it is having some temperature T infinity. So you have a velocity boundary layer, you have a thermal boundary layer which is simultaneously growing. So if you are interested in the stagnation region for the cylinder, what is the variation in the Nusselt number. Okay. So now as we already shown, you can describe that by the stagnation flow m equal to 1, the same correlation will apply for this region as well. Okay. Now x is defined in this particular manner, okay, where this is your r, this is your origin, okay. So now it is not so convenient to operate in terms of local x for a cylinder and sphere. What is a more convenient characteristic length instead of x? Diameter, okay. So usually when you talk about cylinder, flow path circular cylinder, the characteristic length that is chosen is the radius or diameter of the cylinder, okay. So therefore we can transform your local x into terms of r, similarly in the Reynolds number also, and we can define a Reynolds number based on the characteristic length which is the radius of the cylinder, okay. So if you do the transformation, so you already know, so how do you do this transformation? You already know that your Rex is defined based on u infinity x into x by nu. So this is the definition of your local Reynolds number right now. So where you are defining based on your local velocity. Yeah, that's how we have to transform. We'll see how we will transform it, okay. So now you can replace this as you can write this as 2 u infinity. You can write your u infinity in terms of u infinity of x in terms of 2 u infinity x by r. So this is your local velocity profile related to the free stream velocity profile for the stagnation region, okay. So you can substitute for u infinity in terms of the constant free stream velocity x and r, okay. If you do that, this will be x by r into x by nu, okay. So now what I can do is I can multiply and divide by r, so I can say that this is r and there will be an x square by r square, okay. So therefore this is how my local Reynolds number is related to. Now I can define this as my Reynolds number based on the radius of the cylinder, okay, which is nothing but u infinity r by nu. This is the constant free stream velocity, okay, and the characteristic dimension is the radius. So now I have transformed from the local velocity and the local coordinate, I have transformed that to constant velocity and a fixed coordinate, okay. So the fixed dimension here is r, okay, and you have a factor x square by r square. Therefore if you substitute, you can find that your current nux is also hx by k, right. If you substitute for rex from there, you can finally write nu in terms of the radius, which is nothing but h r by k. So you have a 2 square root of 2 which comes out and multiplies with 0.57, that becomes 0.81, and this will be r to the power half and your Prandtl number to the power 0.4. Okay, so this is what you finally get in terms of fixed dimensions r, and so this is the expression for the cylinder when you look at the stagnation flow, okay. So in terms of the cylindrical dimensions, okay. So you can simply transform from your local coordinate to the cylinder's fixed dimensions, which is basically the radius, Okay, the same way you can also do that for sphere. Okay, for the case of 3-dimensional wedge flows. Okay, now whatever we were discussing so far are two-dimensional wedge flows. The same two-dimensional wedge flows can be transformed using what is called as a Mangler's transformation. Okay. So if you happen to go through the boundary layer theory by Schlichting, okay, so he talks about 3-dimensional boundary layers. So there one way of deriving the similarity solution for 3-dimensional wedge flows is to take the 2-dimensional wedge flow solution, apply a particular kind of transformation called Mangler's transformation, and you will get the similarity solution for 3-dimensional wedge flows. And for that particular case where m equal to 1 for 3-dimensional wedge flows, that is the stagnation region, stagnation flow for 3-dimensional wedge flows, and that will be similar to the stagnation region flow for sphere in 3D. Okay, like we have equivalent to a 2D wedge flow stagnation region, we can correlate that to stagnation region of a cylinder. Same way a 3-dimensional axisymmetric wedge flow stagnation flow can be correlated to the stagnation region of a sphere. Okay, so you can also have a similar relationship for Nusselt number for a sphere from the applying the Mangler's. So anyway, Mangler's transformation is beyond the scope of this class. So I am just giving you an idea that you can also do that for 3-dimensional wedge flows. Okay, so I think with that we have more or less covered the flows with pressure gradient terms. Any questions so far, whatever we have done?
So if you want to find out the transport at that stagnation point, how can we denote the R is same at the theta equal to pi by 2 and
yes, yes. So this just only says the Nusselt number in the stagnation region. That's it. That is only for that. Okay. So it is not really, you are not really varying the x, because variation in the x is actually confined to a small region near the stagnation point. So you just say that what is the stagnation point Nusselt number, for example. Okay, so based on the free stream Reynolds number and for a particular value of Prandtl number, you directly get the Nusselt number in the stagnation region of a cylinder. Okay, you don't once again look at the local variation of the Nusselt number and things like that, because the stagnation region is a very small region, correct? So the next class on Tuesday, what we will do for the same wedge problem. Okay, now the wedge problem that we have taken, we can add one complicated boundary condition, which is, so far we have assumed that your no slip exists at the wall, which is correct, but it is quite possible you can have some small vertical velocities at the wall, correct? So this is your local coordinate x and y. So therefore you can have your v velocity and u velocity at the wall. Anyway, your u velocity is equal to 0 because it cannot slip tangentially, but it is quite possible that you are blowing or you can suck. You know, this is called flows with transpiration. Okay, so this is a typical flow with transpiration. So in that case, you can have a small value of vertical velocity at the wall. It will not be that much, but it will be small enough. So typical applications are if you are looking at boundary layer separation control. Okay, so typically you can blow some small velocity, okay, in order to control the separation point, or if you have a massive separation, you can suck the separation bubble by means of flow suction, and therefore you can avoid separation. So typically in like airfoils, you can do this kind of flows to control the drag and stalling of the airfoil and so on. Okay, so these are extension of the same Falkner-Skan solutions. The same solution or same equation, the similarity equation what we derived will exist and it hold true for this case also, only the boundary condition will now change. Okay, so far we have said at y equal to 0 v equal to 0, but now will v has a small component, so that has to be included and we can use that as a more generalized solution. Okay, so if you do this solution, this will be the most general solution for whatever we have seen till now. Okay, that includes all kinds of configurations, also different kinds of boundary conditions. For limiting case where v equal to 0, it becomes the solution that we had derived till now. So okay, we will look at this particular case in the next class, and with that we will complete the similarity solutions. Okay.